Screen ಕಾಣ್ತದೇನ್ರಿ? ಕಾಣಿಸ್ತದೆ ಆಡಿಯೋ ಇದೆಯಲ್ಲ?
Sir.
Okay. Good afternoon. Hope we are got delayed. Last class we were discussing about the electromagnetic radiation and their environment, and also the last regarding the amount of energy which is radiated from an object. Like 3 laws we discussed: is the Planck's radiation law, Weil's displacement law, Rayleigh-Jeans law. Let us concentrate on black body concept. There is topic number 3, where it involves with the emissivity and radiant temperature, electromagnetic spectrum, and wavelength bands of that kind. We'll go in general to a great extent, where in first part of the electromagnetic energy or electromagnetic spectrum, we discussed with these 3 laws. Black body concept also comes in such a way that there's also dealt in the earlier electromagnetic energy spectrum. Black body in general, say every body is said to be either gray body or maybe a black body, depending on its emissivity, they can call, or depending on its emissive power, or depending on its power either to receive the energy and also to transmit or maybe re-radiate back energy to its environment or maybe the surrounding. Black bodies are the one. So we usually might have got the concept of having a cavity, having a black, some spherical shaped object with cavity inside, and if you allow all the radiation to enter into the black body, first it absorbs. After it absorbs, the radiation will be emitted from a small orifice, they can call small orifice, in all wavelengths, in all the solid angle, to a great extent what you learned so far in your either graduation or post graduation or maybe in school days to a great extent. That is the case. The sun is also said to be a black body, or stars are also said to be a black body. If not, whatever the radiation falls on the black body, if it does not allow the radiation to be scattered or re-emitted back to its environment, we can call them as a gray body. Means some portion of the energy will be trapped, some portion of the energy will be blocked, or maybe will be absorbed and got it locked within that system, and it may be converted into some other form of energy, or it also may be converted into some other kind of an energy in such a way that it may not be emitted in the same wavelength or maybe the same frequency what it got absorbed. This being an electromagnetic spectrum, starting from the range of an radio waves to a greater extent of the gamma rays, or in terms of the frequency either from gamma rays to a neutron energy till to the extent of the radio waves, all wavelengths are part of black body radiations or the black body radiators. We'll see that one after the, then let's how one can proceed. If this is the case, how is that electromagnetic energy gets radiated or electromagnetic radiation generated? The right side you can see the spectrum that's covering from long waves to the short waves. Either in terms of frequency can go or in terms of the wavelength, you remember. But visible part of the spectrum is very small. Final wave bayar they can call, violet to the red they can call. If you allow the prism to allow the radiation to pass through, or if you allow the white light ray to pass through the prism, it gets dispersed. That depends on the dispersion angle or also the wavelength. Actually, red gets more deviated than that of the blue. That is why blue color of sky is mainly because of, even though it is saying that Rayleigh scattering, mainly because it is less scattered, less deviated from the deviated while reaching the Earth's atmosphere compared to the other radiation. But during early hours of the morning or maybe the late evening hours, the sun appears to be red mainly because the red gets scattered more towards the earth and rather than the other color of the sky. Okay. Here, how electromagnetic radiation is generated, we broadly can specify them either in terms of the radio waves to a great extent, or microwaves here within this region, or maybe visible small portion of spectrum. Radio waves are generated by periodic changes in the currents of electric charges in wires. For example, if you allow the wire electricity to pass through the wire, okay, radio waves gets generated. Maybe you can call it as the combination of the E and F, E and B actually, E and F that can be generated in a wire. Microwaves are generated by electron tubes, not by the same technology that uses the motion of the high-speed electrons from one point to the another point, which are specially designed structures to generate either the electric or magnetic field, or maybe the combination of the electric magnetic field put together to a great extent. But whereas the visible light, even though we are handled with the visible light so far, actually how it is generated is really a question, is challenging issue. Such a way, visible light falls within the high frequency wave in the infrared to the invisible, which are generated by molecular excitation or maybe de-excitation. Any molecule, if or atom or an element itself, if it receives the energy, either maybe thermal, mechanical, or visible, or any kind of energy, if it transfers or if it either excites or de-excites, during excitation and de-excitation, it emits the radiation. That radiation falls within a wavelength of about 400 to 700 nanometer, or about 4000 to 700 angstrom. It falls under the spectrum of the visible radiation. Okay. Even the molecules which can go for vibrational and orbital rotations also emit the radiation invisible. Okay, in the form of a visible. Don't put the invisible as a single word. And even some of the radioactive elements which can during decay emits the radiation, particularly the gamma radiation, they can call actually, that falls under the spectrum of about 400 to 700. What it is listed in the form. Okay. The emitted frequency is exactly related to the energy difference between the two energy levels of those molecules. But at the same time, heat also a kind of an energy. Heat is the kinetic energy of the random motion of the particles in a matter. The random motion results in the either excitation. This excitation means transition between electron to the electronic level, or maybe a vibrational level, or maybe rotation level, or maybe the combination of the any of these two, either electronic, vibrational, and rotational, due to the collisions which are followed by the random emissions of electromagnetic wave during the decay. Because of its random nature, this type of energy transformation leads to the emission over a wide spectral band. That is why we can call it as a heat band. Heat band, particularly thermal band to a greater extent. Being this, what thermal radiation can have? Can we say that a body at any given temperature or a body at a temperature may be read as or treated as the thermal radiation? For example, if the body of the temperature is about 10 degrees Celsius, it emits the radiation. Sure. If it is at 20 degrees Celsius, still emits. If it is 100 degree, fine. Even if you go to the extent of 1000 degrees Celsius, emits, fine. 6000 degree Kelvin, even the temperature of this photosphere of the sun, it emits. If you go with the lower side, can you expect that 0 degrees Celsius where the objects emits radiation? For example, water, if you cool them to an extent of the 0 degree, it becomes the ice. Maybe liquid water, you can call liquid water gets converted into the ice. Ice means as a solid ice. And can we expect that the radiation will be emitted by a body if it is maintained at 0 degree Celsius? Sure, yes. Because if you take the ice cubes, actually, ice cubes appears white even though their temperature is 0 degree Celsius, mainly because whatever may be the radiation which falls on that, part mostly gets absorbed and partly gets reflected back to a greater extent. Even if you go for sub-zero, minus 10 degree, minus 20, minus 40 degrees Celsius, still they emit. But if the object is at a temperature of about absolute zero of minus 273.15 or 27 degrees Celsius or 0 degree Kelvin, they can call, they may not emit the radiation because molecules or atoms may not under the motion. Means thermal radiation is emitted by all objects which are above the absolute zero of degree Kelvin or above minus 273.15 degree Celsius. Sometimes they will use minus 273.16 also. Let us take it as the lower end of minus 273.15. Here, whatever the spectrum you are getting, this is a spectrum of this type of radiation, that is the intensity against the wavelength. Intensity against wavelength usually follow the ideal black body radiation curve. It's ideal because a body maintained at 6000 degree Kelvin is having a solid curve which is shown on the top. Okay, means against the wavelength. This is the relative intensity. Against, you can see that this is at a temperature of about 6000 degree Kelvin, almost represents the temperature of the photosphere of the sun. Even though the sun is treated as the black body, in principle, it acts like a gray body because the temperature comes to be around 5700 to 800 degree Kelvin. It also shows a spectrum, may not be a curve of the solid curve of that kind. For example, if the tungsten filament, if it is maintained at 3000 degree Kelvin, certainly it is having a peak starting from about 0.1 micrometer, goes to a peak maximum emissivity, peaks at a certain value of about 1 micrometer. Then if you come down, then it can reach to the extent of about 50 to 60 micrometers, sorry, 500 to 600 micrometer of that kind, actually, to a great extent. Okay, here then you can come for the 800 Kelvin for the red hot objects, which are either maybe cast iron or maybe gold, silver, whichever maintained at furnace, they will go to the extent of the red color, particularly a temperature of about 800 degree Kelvin. Or on average, the global temperature of the Earth falls with about 15 to 20 degrees Celsius, 23 degrees Celsius, 27 degrees Celsius they can call, or 300 degree K comes to be somewhere here. And this is for the dry ice, still goes down, and this is for the liquid air, where it is maintained at a temperature of about 79 degree Kelvin. Actually, here two solid lines, you can see that one solid line for the sun and another solid line for the Earth. Actually, just to represent the two things, entities, they are shown actually. But the sun emits maximum light of 50% in the visible region between 0.4 to 0.7, where it is hatched with the gray color. Sun emits the radiation, almost 49-50% of the radiation will be in the visible region. Actually, around 11% falls with the less than visible, that is the ultraviolet and below that actually. But infrared and rest of the part will be occupied by the about 39%, 39 to 40% you can expect. 39% in the ultra infrared and about 50% in the visible, and that is about less than 11% in the ultraviolet radiation of that kind. Because of this, most of the sensors used to study the sun or the activities of the sun are designed at about 0.4 to 0.5 micrometer, where it falls within the visible category. Means can also see that from this curve in such a way that as the temperature goes up from either 79K to about 200K, 300K, or 800K, this peak is at the peak emissivity they can call, peak emission they can call. As the temperature goes up, the peak in emissivity shifts towards the lower wavelength side or towards higher frequency. See that it is moving towards left. If you take between the spectra of the peak emissivity of the sun to that of the Earth, actually 6,000 to 300, almost 20 times more. Peak emissivity in the temperature of the sun and the Earth is almost 20 times more. But peak emissivity, if we expect from the Stephen-Boltzmann law, which is the sigma T to the power of 4, even sigma gets cancelled. Flux for sun to the flux for the Earth, if we expect 600 times to the power of 4 to the 300 times to the power of 4. 6,000 divided by 300 gives you about 20. 20 times to the power of the 4 gives you almost 1,60,000. In the sense, compared to the radiation emitted by the Earth, the radiation emitted by the sun is about 1,60,000 times more than that of that, because of that high temperature. Okay. That beam displacement law shows that the wavelength of the spectral peak is proportional to the, particularly inversely proportional to the temperature. As the temperature goes up, peak shifts towards the lower wavelength side or higher frequency side. What you learned from your school days, the same definition you can carry, but you can also have the capability to analyze the emissivity of the objects depending on their temperature. As the temperatures are higher, certainly peak emissivity should be at the lower wavelength side, as the peak emissivity will move towards the longer wavelength as the temperature comes down. Means to say that if you are having an observations for any of the solid body or an object body, if the temperature goes on reduces, peak emissivity shift towards the right side or longer wavelength side, or quite reverse to a great extent. Being this, if that's the case, what is the black body? What do you expect? Maybe asking like a fundamental questions or maybe basic questions of that kind. Black body we defined earlier in the beginning. Whatever maybe the radiation which falls on the body, if it absorbs all and re-emits back to its environment, without retaining any of its radiation, they can call it as the black body. They don't use the black BLOCK black body, it's a black, okay, in terms of the color also. A black body emits the temperature, which depends emits a temperature dependent spectrum of the light. In the sense, whenever you are expecting the black body, it emits the radiation. Sure, that emitted radiation depend on the temperature. Means for different temperatures, it emits different wavelengths. Here you have seen that if a black body is whatever maybe, if a black body is at about 800 degree Kelvin, it emits about 50 micron. If it is about 200, it roughly it's about 10 micron. If it is at 300 degree, almost about 10 micron. If it is 800 degree, almost about 2 to 5. If it is at about 6000 degree Kelvin, it emits at 0.5 micron. Means the black body is the one where it shows a temperature dependent spectrum of the light, maybe either in the visible or maybe even in other colors or other wavelengths too. Thermal radiation from a black body is termed by a black body radiation, no doubt. Here what happens, for example, at room temperature, so far you are well aware that you accepted the concept of the room temperature. If that is a room temperature in summer, room temperature in winter, room temperature in rainy season varies. Room temperature over Delhi, room temperature over Bangalore, room temperature over Polar also varies. Room temperature means which temperature I have to take. Means if it is at during winter, maybe shall I go ahead with the 10 degree, 12 degree of that kind. Even room temperature over the USA and room temperature over India. Means here the regions with the high latitude and the low latitude, if you expect, certainly the temperatures over the high latitude are relatively cooler. And if I take the room temperature over the polar region, certainly it will be sub-zeros. Okay, room temperature means it is an average temperature they can call, not the room temperature maintained at an air condition, which is having a comfortable zone for the human being to live. At room temperatures, of the order of about 20 to 30 degrees Celsius, or maybe about roughly 300 degree Kelvin, what we expect, more or less, okay, not beyond that limit. Black bodies emit mostly the infrared light. Okay, but as the temperature increases few hundred degrees beyond that limit, black bodies start to emit visible wavelengths, either maybe shorter and still further shorter to a great extent, starting from red to orange, then to yellow, then to white, somewhere combination of them, then to the blue, or red, orange, then yellow, then white, then blue. Here you can see that this curve you expect here. Let us concentrate on the diagram in such a way that X and Y only on the magnitude or intensities actually, starting from dark blue till to the dark red you are expecting. If you go at the top, as the wavelength decreases to the top, and it has to come down. This is showing a shape of almost like a parabola to a great extent. But at the same time, concentrate on temperature also. Starting from a temperature of about 1500 degree for the red color, about 2000 for maybe an orange color. Still, if you go for about 2500 3000 for yellow color, yellow means yellow peak you are observing for the sodium lamps, about 5890 angstrom to a great extent here, somewhere here, 5890. Okay, 5890. Then still, if you go come at lower end actually with the higher temperature, 4000 degree Kelvin, 6000 degree Kelvin, and sorry, 10,000 degree Kelvin of that kind. 10,000 means it is at infinite temperature. Means blue, if you expect, if you might have seen the Bunsen burner, which is burning with the flame, always the hot appears to be blue. If you expect that, is it red is hot or blue is hot? Can you send in a text message? Red is hot or blue is hot? Which is hot?
Blue is hot. So blue is hot.
Blue is hot.
Blue is hot.
Okay. Means that's why all flames are burning in the blue color. We should not get confusions. Red hot, we have studied from the school days, very at lower stage actually. But as the wavelength is increasing, wavelength is decreasing, or maybe energy or intensity, energy is increasing, frequency was also a higher frequency for the blue. Blue is more hotter, relatively hotter compared to that of the red color. Wavelength of black body radiation depends on temperature of the black body. See that wavelength of black body radiation depends on the temperature of the black body. If black body, how you expect? Being this, how that thermal channels of the electromagnetic spectrum can be there? You're having a different channels. Channels with different domains they can call actually. All colors will not fall in. For example, this is the violet, falls with somewhere here, maybe an indigo, blue cyan, maybe red covers the white spectrum. relatively wide spectrum, starting from 625 nanometer to about 740 nanometer, more than 115 nanometer of that kind actually. In orange, a sharp line somewhere here. Green is also between 522 to 565, and indigo is very narrow, shallow of that kind, violet to a great extent. What happens here? Thermal channels, if you expect, this is towards the photons of the energy, which is the atmosphere's capability to allow the radiation coming from the sun to reach the surface of the earth actually. Like almost at the top of the atmosphere, gamma rays, X-rays, ultraviolet rays, which are blocked or stopped by the upper atmosphere. Best observation from the space. If you want to study the X-rays coming from the sun, or ultraviolet radiation coming from the sun, or maybe extra galactic also, you can't put the sensors near to the surface of the earth. Those radiation, when enter into the atmosphere, interacts with the atmospheric molecules and loses most of its energy, and it may not reach. It is a good boon for us actually. Without the atmosphere, life on Earth is an impossible task. That is why you can't expect the expectancy of the life, particularly on human being, what we are living on as a comfortable zone on Earth, in either in Mars or maybe Moon or maybe Jupiter or Saturn of that kind. The Earth's position with reference to the Sun is placed in such a way that it is quite comfortable and well planned and well treated for the radiation zone. Maybe some organisms like viruses, maybe the viruses, or maybe some algae, something may stay even beyond the temperature of the order of several thousand degree Kelvin, or even at the cooler temperature of about sub-zeros of minus 200, minus 250 degrees Celsius too, to a great extent. That's different. Means if you want to study such type of an environmental radiation, the sensors should be put at above the top of the atmosphere or above the atmosphere, they can call. This is a visible spectrum, which is coming well down actually, means where the absorptivity is quite high here, this gets absorbed, maybe still it reaches. Still see that these are the peaks which you are expecting actually, how it can go. Most of the infrared spectrum are absorbed by the atmospheric gases, best observed from space, if it is the case, if you want to study. Radio waves are observable from there. That is why all communications, particularly satellite communications, is in radio wave spectrum or radio wave domain, they can call. Long wavelength regions and also radio waves, which are also blocked by the radiation, almost about more than 10 meter to about 1 kilometer radiation coming from the space, will also get absorbed. See that the bottom, maybe this is for the near infrared or maybe short wave infrared radiations, medium wave infrared radiation, long wave radiation, infrared radiation. Means in general, a hot object will distribute its emission over a long range of wavelengths, continuous spectrum. Continuous spectrum. Okay. Doing this, what's a black body? Okay, of course, earlier we studied the black body is an idealized object that absorbs all electromagnetic radiation that falls on it, no doubt. No electromagnetic radiation passes through it and none is reflected back. Perfect emitter should be a perfect absorber. Means people also say that you be like a black body. Means if you are good at one task, maybe for example, even grooming in a classroom, you are good at other subjects. If you are good in quantum mechanics, you are also good in mathematical physics. If you are good in electronics, you are also good in some other kind of a subject. If you are good by virtue of your own, you will be good in all. A perfect black body is a good emitter as well as good absorber. In a sense, first it is a good absorber. As soon as it absorbs, it has to emit all the radiation back to its environment. It is a perfect emitter too, to a great extent. Means all radiation which is incident on the black body, maybe don't expect the shape which is shown here actually. Okay, in any shape, preferably a spherical shape of that kind. It emits all the possible radiation back to its surrounding. How it emits, we have to see that. Because no light or even maybe the visible part of the electromagnetic radiation is reflected or transmitted, the body appears black when it is cold. We are calling it as a black body, not by the virtue of the color, by color, because whatever the radiation it falls, it does not allow the radiation to escape. That is why it is called the black. Because it is a poor reflector and it does not allow for the transmission to a great extent. You might have already studied this Snell's law and other laws to a great extent. Whatever the radiation which is falling on that part gets reflected back to its own environment or its own space, they can call, provided if there is if the radiation enters from a media of refractive index, differs in a media of refractive index from one to other. A part gets refracted, means enter to the media, maybe it either bends towards the normal or away from the normal depending on the refractive index, and another part gets transmitted. It is maybe like if you take a glass, a sheet of a glass, or maybe a slab of that kind part. At any amount of the time, the amount of the radiation which is incident on a material should be the sum of the radiation which is reflected back to the same media with same refractive index, and it enters into the media with different in refractive index. Okay, then it has to come out of the media with the same what the radiation which was incident, that should be sum. Observe, means ratio of the radiation which is reflected to the incident is reflectivity. Ratio of the radiation which is refracted to the incident is the refractivity. Ratio of the radiation which is transmitted to the incident gives you the transmittivity of that kind. At any amount of time, if the object is said to be a good reflector, refractivity and the transmittivity should be minimal. If it is a good transmitter, reflectivity and refraction should be the minimal. If it is a good refraction, only it gets refracted and gets absorbed actually, then absorption, transmission and the reflection should be minimal. Means the total amount should leads with either 100% in terms of the percent, or maybe in terms of the coefficient, maybe you can call it as divided by the value what you are expecting. Reflectivity, absorptivity, and the transmittivity of that kind. Black body is a good absorber as well as a good emitter to a great extent. With this, what normally it will go ahead with the case. Black body experiments, one can do that in laboratory. I am sure that those who are involved in teaching might have taught in such a way that some experiments in the laboratory. Here, choose an object here, maybe with some cavity or as a hole for the radiation to escape. And this is a hot object where it is shown in dot. And this cavity, purely of the cavity of that kind, radiation is in equilibrium with its walls to a great extent. And radiation which is emitted, the radiation may be analyzed through the spectrometer. See on the right side a graph or a plot in such a way, particularly the radiance or intensity against the wavelength. As the wavelength goes up, as with increasing thing actually, it shows peak at one particular particular wavelength. For a given temperature of T1, it shows a peak at somewhere here. For a given temperature of another temperature T2, it shows a peak here. Means to say that if the temperature of T2, for example, temperature of the second body is more than the temperature of the first body, peak shifts towards the lower wavelength side. This is only the conclusion what you are expecting. Means an object of controlled temperature contains a cavity which is joined to the outside of a small outside through a small hole. If the hole or the dimension of the hole is very small, the radiation in the cavity comes out to the environment if it is maintained at an equilibrium through the walls. If the holes allow small fraction of the radiation to pass through a spectrometer, okay, the radiation coming out has the same spectrum as that what is inside. Means whatever you are observing here, spectrum actually, which is emitted by a cavity or coming through the cavity, the same spectrum you can observe inside the black body also to a great extent. Being this, note that here the plot of this Planck's radiation law for the two temperatures of the T1 and T2, where T2 is greater than T1 and peak shifts towards the lower wavelength side. Means to say, hotter objects output a large fraction of their electromagnetic radiation at shorter wavelengths. Means most of the hotter objects emit the wavelength or peak in emissivity, they can call, for the shorter wavelengths. It also notes that the strong dependency exists between the temperature and the total emission. Means if you estimate the area under the curve, in the sense for the longer temperatures, the area should be smaller. Higher temperatures, the area should be more. For the lower temperatures, the area should be the less. Quite reverse of that kind. The radiance here, the radiance is nothing but the amount of the radiation which is emitted back. Okay, or the power. The radiance is the power which is emitted per unit area, per unit time actually, per unit wavelength to a greater extent, and should be represented in terms of watt per meter square per meter, they can call, per second. Rate is used. The term rate is used always whenever you are taking a derivative with reference to the time or the ratio of that component with time. Means the time derivative only they can call. Means otherwise you can take the ratio of, derivative of any of the parameters per unit area of per meter square or per micrometer square or per kilometer square, doesn't matter. If it is per volume, maybe metric cube can go, but here radiance is nothing but the amount of the energy or the power which is radiated per unit area per meter square for any given wavelength. That is why one more meter is coming. One more meter is coming, which is having a dimension of the order of watt per meter cube of that kind. This is spectral radiance. Spectrum is nothing but the amount of the radiation or amount of the flux or amount of the amplitude or amount of the energy or amount of the power which is radiated per wavelength or for a given wavelength. Means it has to cover the entire spectrum starting from lower to and higher values to a great extent. The spectral radiance from the pole is independent of the material used and only depends on the temperature of that body. Means whichever. Here see that temperature of the second body is 1.3 times than that of the T1. That is why peak is shifting towards the lower impact. What spectral radiance you can expect? Radiance is the amount of the radiation which is emitted by a body. Spectral radiations or radiance is the amount of the radiation emitted by a body which is maintained at some temperature. Spectral radiance defines as the radiance delta L here containing a small range of wavelengths delta lambda, not all, delta lambda, with an emissivity of L lambda. Here L lambda is the differential form of L with reference to the lambda, delta L by delta L lambda or del L by del L lambda of that kind. Why small portion? Because you can integrate it. That is the main purpose of analyze for the small solid angle, then integrate for the entire body. You will get that how much the emissivity will be there with that irradiance actually. Spectral radiance, particularly in SI units, they will call it as watt amount of energy per meter square per steradian. Steradian is the solid angle subtended through an omega where the radiated flux which is emitted out should be measured. This solid angle remains constant with the angle actually. With whatever with the omega you are expecting, the same amount of flux will be emitted per unit area. For example, if I take here, assume that about some x amount of the radiation which is emitted out, x watt of amount per meter square per steradian per meter. If you go here, the x may becomes an x plus delta x, but if you expect that per meter square and per steradian per meter, it remains same. Means to say that irrespective of the dimension of a cone, either maybe the narrow to a broad, the flux emitted by a body remains constant, particularly in solid angle or steradian angle they can call. The same thing they can expect for the radiance in such a way. Spectral radiance is the radiant flux per unit solid angle, leaving an extended source in a given direction per unit projected source area in the direction along the radiation which is emitted. Or radiant flux can be defined in such a way. Radiant flux, particularly for it is also depending on the wavelength, leaving the projected source area of A with a certain direction theta with the solid angle omega. Means all these three components put together. Means L lambda one can expect in such a way. Ratio of 5 with reference to the omega of solid angle over the area of cross section of that cone times the cos times theta of the angle which is subtended with its normal. So normally watt per meter cube per steradian they can call. For this, three laws will come into the picture: Planck's law, Wien's displacement law, and Rayleigh-Jean's law. Okay, earlier also maybe beginning we might have discussed actually. Just for the continuity, I will repeat. Here, this law describes the amplitude of the radiation which is emitted from a perfect black body. Okay, perfect black body is a black body, but if not perfect, they call it as a gray body. Okay, don't get confusion at the level of the PhD level, actually doctorate level. Such a way, perfect black body is the one. Instead of calling perfect black body, they will call it as a black body. If it is not a perfect black body, you have to call them as a gray body to a great extent. Generally provides the two forms. Either this L of lambda, which is a function of the wavelength, is the radiance per unit wavelength as a function of the wavelength. Or you can also call that as the radius per frequency. If you see nu is equal to c times lambda, you can expect the expression for the nu that should be in terms of the c value, multiply or maybe divide appropriately with the speed of the light. Is the radius per unit frequency, which is as a function of the nu can be shown. This, of course, don't worry with the expression in such a way that here it shows that it is inversely proportional to the lambda, and it also depends on the temperature. Here the terms or terminal symbols used follows the same terminologies of the standard versions, unless you deviate version from that. Whenever you are referring books from either from Europe, Asia, Russia, and other things, you will have the same thing. Temperature for the in absolute Kelvin, degree Kelvin. C for the speed of the light, Planck's constant, and then Boltzmann constant, and this is spectral radiance and spectral radiance. Sir, one class spectral radiance of that kind. Here, intention for the Planck's law is in such a way that it gives us the amplitude of the radiation which is emitted by a perfect black body. Being Stefan's Boltzmann law, it gives us that is the total radiation emitted radiation from a perfect black body, which is proportional to the 4th power of its absolute temperature. T, instead of absolute temperature, if you use the actual temperature without conversions, you may not get the you may not have the validation for the law to that extent. That is why, while using the symbols, the convention should be used in such a way that you have to write the temperature should be in absolute temperature. The value of the Stephen Boltzmann constant, you are well aware, watt per meter square, or to the k to the power 4. What it gives? This is the flux which is emitted. Flux means that is the emitted radiation they can call. The emitted radiation, which is also showing a function of the wavelength to a great extent. For different lambdas, you will get different m value. Means even for a given temperature, assume that 6000 degree Kelvin, it is having some m value. Instead of 6000 degree Kelvin, if it is at about 300 degree Kelvin, you will have the emitted radiation which is showing a perfect lambda of that kind. The amount of the energy which is emitted by an object, such as the sun or maybe the earth, which are the function of its temperature, means the amount of the energy radiated by sun differs the amount of the energy which is radiated by the earth, because they are maintained at a different temperature. This can be derived by integrating the spectral radiance over the entire spectrum, starting from 0 to the infinity, where these are the usual symbols, or we can call it as m is equal to pi times L. Pi is for 180 degree with solid hemisphere they can call. You can't call it as a 2 pi to a great extent. That should be equal to the sigma t to the power of 4. How that is Stefan's Boltzmann law of time. By knowing the temperature, one can estimate the emissivity, or indirectly, you are measuring the flux. You are measuring the energy, you are measuring the power. By knowing the power, you can estimate that the temperature of that object, even though it is at a distance of about 150 million kilometers, particularly the sun. This we discussed earlier. Wien's displacement law gives us in such a way that in addition to computing the total amount of energy which is exiting a black body, we can also determine the wavelength based on the Wien's displacement law. Here in earlier case, we estimated in such a way that we know that the temperature, because of we can estimate the temperature. Here we can estimate the temperature, also we can estimate total amount of energy also we can estimate emitted by the sun or any hot objects they can call. One can also emit the wavelength. How they can do that? Lambda maximum must be equal to k over t, or lambda maximum times temperature must be equal to the constant. That constant is known as the Wien's displacement constant actually. Here lambda m is that the peak in the emissivity for particular wavelength. Peak in emissivity for particular wavelength at about one particular wavelength they can call actually. 3000 degree Kelvin is a function where the maximum emissivity comes to be 1 micron. Okay, here the 4000 0.4 to 0.4. Sorry, here this is for about 4000 degree Kelvin. You can expect emissivity at about 0.6, 0.7. Here the sun at 5000 degree Kelvin emits peak emissivity at about 0.55 micrometer of that kind. Where Earth emits at a temperature of almost 300 degree Kelvin with a 10 micrometer. Means to say, if you want to use some sensors to understand the phenomena, to observe the sun, you have to keep a sensor which is having a more sensitivity at about 0.55 micrometer. Okay, if you want to study the radiation emitted by this Earth actually at 300 degree Kelvin, you have to put a sensor roughly at about 10 micrometer. Sensitivity up to 10 around 10 micrometer to a great extent. If you assume that if you are having a sensor between 1 to 100 micrometer, certainly you can capture the information emitted by the Earth. But if you put the same thing to the sun, you can't expect. You will never get a spectrum, or you will never get any information or signatures which are emitted by the sun to a great extent. Means to say that there is an inverse relationship between the wavelength and the peak emission of a black body and its temperature to a great constant. Means, therefore, as the sun approximately maintained at about 6000 degree Kelvin emits 0.55 micrometer. Rayleigh's approximation shows that it is not the law, being we can call it as an approximation. It is the convenient and accurate description for spectral radiance for a wavelength which is much greater than the wavelength of the peak in the black body radiation, where lambda should be too much greater than, for example, 10 is more than 9, 9 is more than 8, 10 is more than 1. How much more? I have to remember. Too much greater than, for example, if I consider 10 and 1, is it too much? Or if I consider about 1000 to 1, is it too much? Means whenever you are saying that too much, or whenever it is you are saying that much greater than, at least the quantities should be more than by an order of magnitude. Means between 1 and 10. 10 is 1 order of magnitude more than 1. 100 and 10. Of course, sure. 100 is more than 1 order of magnitude than 10. Between 100 and 1. 100 is 2 order of magnitude more than 1. Means order of magnitude you have to expect at least either too much less or too much more should be deviated by its original value by an order of magnitude. Assume that if it is 1 and 9, you can't call it as a 9 times maybe more. Okay, y is equal to 9 times x. If I put actually whatever the value of the x, it should be 9 times more. It is not changing by an order of magnitude. You can say that so many times more. Maybe 2x, 3x, 5x, 9x, fine, no problem. If I put a 10x, okay, you can say that it is 10 times more, there is no doubt. But at least you can say that it is too much greater than by an order of magnitude is more. 99 times x, for example, almost about a 2 order of approximation, 2 orders more than that, what the original value of the x can take place. Here, if that is a case being an L lambda, it is inversely proportional to the wavelength, or can also expect it is directly proportional to the what we can call frequency. Approximation is better than 1%. Okay, this the Rayleigh-Jeans approximation are saying better than 1% when this hc by lambda kt, where you are getting here, this kt you can make hc by lambda kt, either it should be too much less than 1, or the lambda should be more than 0.77 times temperature should be there. Sorry, I missed one temperature here. Should be 0.77 times T of millikelvin, because here milli is there, Kelvin is there. That is why it should be there. Means, for example, for a body with 300 degree Kelvin, for as far as the Earth is considered, the approximation is valid when wavelength is too much greater than 2.57 micrometer. If it is less than that, it may not have the validity. In other words, this approximation is good when viewing in the thermal radiation from the Earth over the microwave. Compared to the microwave, if you use this expression for the thermal emission, then Rayleigh's law can approximate it to a great extent. As far as the energy coming from the sun is considered, it emits in all the spectrum of electromagnetic radiation. See here on the left side, 5770 to almost 6000 degree Kelvin. It is a thermonuclear fusion reactions which are happening, which generates a short wavelength radiation. If it allows to fall on the Earth, okay, it will transmit through the space with a speed of almost speed of light, and part gets reflected back by the atmosphere and the solid Earth, okay, to the space, reflection of the short wave, and emission of the long wavelength will happen. Once, see the difference between reflection, refraction, and transmission, you should be well aware. Reflection is the one, if you're getting the same amount of the radiation, sorry, not amount, if you're getting the radiation reflected back to the same media without changing the refractive index, you can call it as a reflection. For example, total internal reflection will also happen. Means total internal reflection, how it's happening in an optical fiber, that is the region in such a way that if any radiation incident on the optical fiber with grazing angle beyond the critical angle, whatever the radiation you are sending, that will be reflected back. Means most of the radiation gets reflected back. That is why it is called a total internal reflection. Okay, even though refracted ray will not go for refraction, the technology is achieved in such a way that the difference between the core and cladding is in such a way the refractive index allows if it has to move from the denser to the rarer media. While moving that, most of the intensity of the light has to fall back to the same media or medium they can call same medium. If it falls back to the same medium, then the entire amount of the radiation will be reflected back. So reflection will happen totally. That is called the total internal reflection. Because of the total internal reflection, the communication is possible through the optical fibers. Even if they absorb a small amount, a small point followed by 5 zeros afterwards, one if we expect the loss, certainly the communication through the optical fiber was a miserable condition. Okay, forget about that. Here my intention is that portion gets reflected back. Portion gets refracted means it enters into a media, maybe absorbed or absorbed to a great extent. Another portion gets transmitted. But scattering is the phenomena. We will discuss in next class to a great extent. Scattering is a phenomena. What happens? A molecule or an atom or an element or a media, it has to absorb the energy which is incident on the object, and once it receives the intensity of the radiation which is on that object will be reflected back to its environment. It will never stop. It will never stop. Means the radiation or the amount of the energy which is incident on the object will be scattered back to its environment in all the solid angle throughout the sphere of to a great extent. To a great extent. Thermonuclear to a greater extent. Here on the right side, you can see the spectrum between the two sun and the earth. So earth emits 10 micron and sun emits 0.55 micron. What I told you to a great extent. This is the concept how it goes. This spectrum we have seen. Earlier I told about 11%. I told the same thing. The sun emits the 7% less 11% in the less than 7% in the ultraviolet, about 44 to 49% in the visible, and 37 to 39% in the thing, 11% in the far infrared, less than 1% with microwave, TV, short waves, AM radio waves, everything. It scans from almost about 0.001 micrometer at the lower side to a greater extent, about more than 1 micrometer to a greater extent of more than 100 meters actually. Okay, 100. Young energy from the sun is in such a way. The same thing. Maximum radiation emission is almost 41% lies with the visible 0.4 to 0.7, less than 0.4 micrometer with the 59% here, and large components of high UV is emitted 39%. And that this concept is used in the remote sensing, particularly in understanding the Earth and its features actually from a satellite. Here, even within the visible region, about 9% falls with this, about 41% here, somewhere here, and 50%. Right. Means ultraviolet is about 9 plus few percent, and sun to the earth incoming short wavelength radiation from about 6000 degree Kelvin with a dominant wavelength of about 0.48. For this, you can work it out either 5800 degree Kelvin or something like that. If you use 6000 degree Kelvin, you'll get 0.48 micrometer. Sensor should be up the peak at 0.48 degree. Okay, or Earth to the space. If the Earth emits radiation to the space in the long wavelength region at a temperature of about 300 degree, the wavelength falls to be around 9.66 or about roughly 10 micrometer to a great extent. Earth emits the wavelength at 10 micrometer, but Earth receives the wavelength to a greater extent of about 0.55 micrometer from the sun. The same case here we have shown in different spectrum. Just glance it and remember how that works, particularly in terms of the concept wise. The radiation emitted by the sun scales from 10 micrometer to about the 0.01 angstrom of that kind, almost gamma to n microwaves to a great extent. Visible is small spectrum, falls on the earth, and here photon energy, which is in the visible region, scans from almost less than about 4.5 electron volt. Within the visible, for example, if I put photons of wavelength, particularly in nanometers 400 to 700, what you are expecting in terms of the energy around 3.2 to about 1.7. 1.7 electron volt to 3 electron volt is the energy of the photons in the visible region. Particularly, it is also maintained at a temperature, they have to say that actually. Means ultraviolet, violet limit is there at 400, blue, because it is not shown in black actually, but still you can expect. I got this curve back actually towards once again, mainly to see that in such a way, black body radiation curves for several objects, including sun and earth, approximately 6000 K to 300 K appears to be as a black bodies, otherwise gray. As the temperature increases, fine, peak shifts towards the lower wavelength side, and area under the each curve, for example, here either for 79K or maybe 6000K differs. Curve may be sum to compute the total radiant energy exiting or leaving that object. The total amount of the energy emitted is the summation of all or integral part of all the wavelengths put together. In real materials, what happens? Real materials are not black bodies, like either iron or maybe copper or table, whatever the objects you are seeing around you. It describes the in terms of the emissivity. Emissivity is nothing but how much the radiant energy is emitted to its environment to the amount of the energy which is incident on it. Describes the actual absorption and emission properties of the real objects, or even maybe you can call them as gray objects if they are not black bodies. They show the dependency on the wavelength. For different wavelengths, the different emissivity should be there. It is a function of the lambda, which is also the ratio of the energy which is radiated by the material to the energy which is radiated by a black body. Radiation emitted by a body to the radiation emitted by a black body at the same temperature, if we expect. That also gives us the emissivity. Emissivity for a black body is that whatever may be the energy which is received will reflected back. Then emissivity should be equal to 1. Absorptivity is also equal to 1 for black body. Emissivity is also equal to 1 for perfect black body. If the emissivity is 0, you can call it as an emissivity is 0. What will happen? There is no emission. Only the absorption should be there. It is a good absorber. You can call it as a gray body of that kind. If entire thing gets emitted, no absorption at all, again you can call it as a gray body to a great extent. But anyway, the values will vary from 0 to 1 depending on its wavelength or depending on its temperature. Gray body is nothing but an object that reflects a fraction of the incident radiation, 1 minus epsilon times lambda. 1 minus epsilon times lambda of that kind. Real metals, how they are showing that. The top one shows that perfect black body. This is for the 0, no reflection at all. And this is for the gray body in between actually. This is the selective radiator they can call. You can expect at any wavelength, you can expect the peak of that kind. It's the same spectral radiant emittance if you expect. Okay. Here how that it has to vary. Both are one and the same thing, but it is shown in a perfect black body. As the temperature goes up, peak shifts towards the shorter wavelength. These are the different materials. Why? Because copper gives emissivity at some wavelength, aluminum gives at another wavelength, gold gives at another wavelength. Depending on the periodic elements which are available in the periodic table, you will have different peaks. Okay, water, for example, here see that this is for the entire spectrum. Okay, but the thing is that the x-axis is not in terms of the wavelength, it is in terms of the wave number. Nu is equal to C by lambda, what you are expecting, C by lambda. And this is the percentage of emittivity or emissions they can call. Emissivity is ratio of the radiation emitted to the radiation which is incident on it. For a perfect one, no objects will reach this 1 actually, and they will not go for 0 also. They are having some value between 0.7, to about 9. What is shown in the curve. Okay, organic bare soil, greenhouse, maybe green wooden savanna, different materials are having a different spectrum of that kind. Based on this peak, one can identify the existence of the materials. This is, you can show that it's maybe a surprise for you. On the right side, you can see the one index scale starting from about 1 lakh degree Celsius to about 1000 degree, 1000 to about 10,000 degree Kelvin. One order of magnitude, 1000 to about 10,000 degree Kelvin. If it is at a dish, you can expect that temperature should be about 1000 degree Kelvin. If it is slightly yellow, about 2000 to 3000 degree Kelvin. If it moves towards the whitish color or maybe a little bit bluish in color, about 6000, 7000 degree Kelvin of that kind. The temperature of any of the lava flow, this is the Paco lava they can call. This is the image what they have got it actually, a real picture image, can be estimated by observing its colors. If by seeing the color, they can estimate that what must be the kind of a temperature where that material is burning or maybe emitting the radiation. These results agrees well with the measured temperatures of the lava flow, because they can't go and put the thermometer to take the measurement actually. Okay, thermometer need not be a mercury thermometer. Thermometer is a device as a sensor where it can sense the temperature in such a way that how it changes as a function of the wavelength to wavelength. Thermal radiation, you can see that thermal cameras and imaging systems which can respond to the infrared to a greater extent. Goggles looks like a cooler because these are the glass materials of the temperature lesser than that. Human body temperature slightly more than that. Maybe the cloths what they are wearing, the bluish in color, the cooler temperature. See that facial expression goes with the higher temperature of the human body. Thermal cameras and imaging systems respond to the infrared radiation and suitably calibrated for its emissivity to a great extent. It can produce images of the surface temperature of all the bodies, but it will never take the picture well inside. This picture, false color is used in the display. False color in the sense it is not red and black and green of that kind. That is why it is called it as a false color actually. Thermal remote sensing is a good tool to sense. That is why how that sensors are kept in a satellite to study that. The strengths or maybe the advantages is that it is a good resolution we'll get with good accuracy, and it is a long run, more than long 20 years we are using this. But weakness is that if we see all satellites are above clouds, means the clouds may go up to about 15-16 kilometers, at most about 20 kilometers in the troposphere. Maybe next class or maybe another next class we will see that how that atmosphere is classified in terms of the temperature and how that they are ruling the radiation level they can call. Okay, if clouds may go up to about 20 kilometers, so, but still some clouds will exist at the mesospheric height. They can call it as noctilucent clouds, NCL. Noctilucent clouds, NLCs. Noctilucent clouds at a temperature of, at a height of about 60 to 70 kilometers in the mesosphere. Their formation of those clouds is different. They are not from the water vapor to a great extent. Water vapor will never cross the tropopause of the order of about 15 kilometers or about 10 kilometers over the polarizations. What happens, weakness is that if there is a cloud, there are clouds, if you keep these at, you may not observe it at least. And atmospheric corrections are very much required. Such type of corrections one has to apply. Okay. For example, this is the example took it from the remote sensing background. We can go ahead with any kind of an example here. Satellite is kept here. The forests will also emit the radiation like dry forest, wet forest, or maybe thick forest, or maybe thin forest, or maybe bare soil with a different type of a material, either maybe black soil, gray soil, blue soil, green soil of that kind, or maybe the atmosphere maybe with clouds, without clouds, maybe with enough water vapor content, or maybe less water vapor content, whether humid atmosphere and non-humid atmosphere. Even buildings may be covered with the different kind of a material having a different reflectivity. These types of things one can obtain with the image to study the behavior, like atmospheric behavior or material behavior they can call. Thermal satellite structures or sensors they can happen. This is one broad view I put actually. See that this is in the Gaia region. This is the shortwave infrared region, like almost about wavelength of 30 meters, and this is the infrared region actually. Infrared. The broad spectral coverage here and high spectral resolutions of this one ASTA they can call. Means it is the advanced spaceborne thermal emission and refraction radiometers they can call on Terra. Terra means on Earth actually. It was launched in 1990 and how it has captured the information they can call. Landsat is for the land mass and the Terra is for the Earth. Aqua is for the ocean they can call. The same satellite will not work, same sensors will not work for the Earth and ocean put together to a great extent. Some sensors are more sensitive and gives very good information over the ocean. They can call it as an aqua, and some sensors are very particular about the land mass to a great extent. Which is having a good space coverage for surface mapping and monitoring of the dynamic conditions and the temperature change. Here, these are used for monitoring the glaciers, movement of the glaciers and ice sheets, and monitoring the volcanic eruptions whenever it occurs, and identifying the crop stress. Crop stress is whether healthy crops or not actually. Even they can estimate that the growth of the crops also from the satellites, even though they are at a greater height of a few hundred kilometers. And determining the cloud morphology, whether thick clouds, thin cloud, white cloud, rain-bearing clouds, non-rain-bearing clouds, or dangerous clouds, or silver clouds of that kind, and physical properties of all of them put together to a great extent. And wetlands evaluation also one can estimate. Thermal pollution monitoring also they can expect. Means that is the urban highlands they can call. Bangalore is one of the urban island they can call compared to its surrounding areas. That is why we are getting good rain. Coral reef degradations, surface temperature mappings of either soil and geology, and measuring the surface heat balance. These are some of the features how that sensors can work. Sea surface temperature can also be measured. See that whatever it is appearing in red color is with higher temperature, whatever it is with lower temperature, excluding the landmass. Landmass is shown as the white color actually, and lower temperatures are shown in blue color to the indigo color. This calibration is very much required. Now, here these are the regions. This is the region called the tropical convergence zone or intertropical convergence zone. ITCs you can call. These areas are associated with the low pressure or high temperature zones, or the high altitudes are with the high pressure with the low temperature, and wherever this march fast during the Tropic of Capricorn to the Cancer, it brings the enough moisture which can move from 23.5 degree north to about 23.5 degree south, makes the earth to be a balance. Here you are getting the much rainfall during this season, maybe the depressions over the Bay of Bengal, where the Bay of Bengal and the environment around the Bay of Bengal requires a good psychiatrist and a physicist to look into the phenomena. Those physicists are known as the meteorologists nowadays. The sea surface temperature is an important geophysical parameter which provides boundary conditions which are used to estimate the heat flux at the sea surface temperatures or interface between sea and the air. On global scale, we are having a huge model systems, climatological modeling systems, to study the Earth's heat balance. See, some areas are warmer, and it is always getting warmer and warmer at our equator, and cooler over the polar regions. This will never be in balance. This heat has to exchange from hotter to the cooler zone. That cell is known as the Hadley cell, they can call Hadley cell, and there should be balance. And insight into the atmospheric and ocean conditions through certain circulations, they can call. Huge circulations are named as either El Nino or La Nina, that is particularly on the Pacific Ocean. On local scale, somewhere local, sea surface temperatures can be used operationally to assess the eddies. Eddies means small disturbances which are occurring there, and also fronts and upwelling navigations, particularly for ocean navigations, to track the biological productivity. For example, assume that this is the from here till to this extent we are the what we can call east coast of India or Asia, east coast of Asia till to the west coast of USA, you'll get in Pacific Ocean. Almost it covers about 16 to 18,000 kilometer horizontally, 16 to 18,000 kilometer. In the middle of the ocean, if the temperature anomalies happens actually, due to the temperature anomaly, you'll get two kind of major events. One is El Nino, another one is the La Nina. El Nino is referred to as the drought. Whenever El Nino occurs over Pacific, you'll get a drought over Asia. Whenever La Nina occurs over the middle of the Pacific, certainly you will get the good rain they can call. Need not be flood, maybe good rain. But there are out of last 120 to 30 years of the analysis shows that in such a way, even though maybe a good rain, El Nino happens over the middle of the Pacific, sometimes we may get good rain. Even though La Nina occurs over the middle of the Pacific, we may get a drought also. Means to say that out of 130 years, maybe 20-25 years, you can get El Nino and La Nina of that period. The El Nino La Nina periodicity happens to be about 3 to 8 years, 3 to 8 years of that kind. On average, you'll get every 4 years will be a cycle of about good rain or maybe drought to a great extent, and it can track the biological productivity. For example, in the middle of the Pacific, if it is a La Nina, you will get good fisheries for the eastern part. Means wherever good rain occurs, all fishery products and other things will move towards the east coast of the Pacific, and the biological activity will prolong for the marine creatures. Sea surface temperature can also be monitored. It is the same case what I shown in the landmass. Maybe the greater latitudes looks like whitish in color. Again, these are the images brought it from the satellites. Thermal radiation from the Earth actually here. See that these are the high temperature zones. MODIS is one of the spectrometer for the landmass. See that this is monitoring the ice sheets during the polar winter, how it has to happen. During polar darkness, cannot give the visible images from the Antarctica. That's why one has to go for the thermal images. Even ice sheet movement also can be monitored. See, this is not a single experiment, or this is not a single campaign to make these single observations, or maybe observations which are monitored for continuously for a single stations. Satellites, by that virtue, uses the broad view of the entire globe, how it is behaving. Fire monitoring can also be done because we can't take satellites if they are observing any such type of an images. Some precautionary measurements can be taken by the concerned agencies. Oh, good. This is the temperature of the Saturn's moons. Away. Means did not be on the Earth. Even if you take such type of an images, for example, this is observed between 15 to 17 microns brightness. This is derived from surface temperature, how the temperature can go. If the same thing can be dealt in such a way, see that here the temperature somewhere here whitish, whatever you are expecting is in the form is in the range of about 90 to about 100 degree Kelvin. Okay, wherever you are getting blue color, these are of the lower temperatures about bluish color 70 degree Kelvin, 70 degree Kelvin. This is visible image of the Cassini from the ISS camera, how it looks. Which are taken by the composite infrared spectrometers on board of the Cassini spacecraft. Means only one image is not sufficient. They will have multiple images, then overlap one each other. Then they will draw this type of the pictures to get the actual information of this celestial bodies to be at exchange. Thank you. Thank you one and again. Any comments? I will welcome right now. Otherwise, you can drop a mail also. We'll stop sharing the screen and wait for your queries if there are there.
Sir, I'm logging in through another person's ID. I'm present, sir. Even in the last class, I'm Sridevi.
Yeah, fine, no problem. Thank you.
Sir, what is the difference between spectral radiance and emissivity?
What is the difference between?
Spectral radiance and emissivity. Emissive power, emissivity.
Spectral radiance is nothing but the radiation emitted at per unit area for a given wavelength. Emittance and absorptivity, they are different. Photography and absorptivity are different. Photography is a technique used to have the photography by the virtue of receiving the radiation. Okay, but for example, sun is the source. Source emits the radiation. The spectrum emitted by the source differs from the radiation. Spectrum obtained for the observers. In the sense, even though the sun emits the radiation, we have to estimate the emissivity. But how we are estimating the emissivity? We will keep a detector. That a detector absorbs the radiation emitted by the source. It is an indirect way of analyzing. We are analyzing the what we can call absorption spectra of in a material or in a detector. Thereby indirectly we can calculate. We are calculating that how much the emissivity should be there. I don't know whether you got it or not. Since let it be a source, let it be an target, let it be a detector. Okay. If you allow the radiation to pass through the material, target material, the target material absorbs the radiation. Okay. And after whatever it is transmitting, that radiation should be monitored. Means you should know the two kind of values. One is the total radiation which is reaching before it gets interacted, and the radiation which is undergoing a treatment. The difference, not the algebraic sum or difference actually. With empirical relations, you can expect in such a way that how much the energy is lost or how much the energy is flux is lost. That loss in flux, we are calling it as an absorptivity.
Okay, sir.
There are no queries. Shall I end the class? Thank you. We'll meet in the next week, hopefully.
Okay, sir. Thank you, sir.